So, good afternoon. So, I guess you're already learned. Where is this place? Quite distant from our usual building, but closer to reactor. Interesting enough. So, another tale, another lecture is coming. And this is not in Khmelnytsky set, it's something which we have added. I added it, and the reason for that, well, it was very interesting to me. When I was a student of your age, it has great significance in many areas of physics. And what is especially interesting for us, it illustrates how quantum mechanics, how theoretical physics can be useful in very different settings, actually with the same formalism, with the same way of thinking. Well, one can say that waves provide enough example. Yeah, but waves are a kind of all physical. What will happen today, we provide connections between the systems, analogies, which are purely theoretically based on something which doesn't have any chance to be equivalent. Really very different works, quantum and classical. Right, so in one word we have this little bit tasteless analogy, typical German, between dead and alive cat. Complex sense, superpositions of wave functions. On another side, we are dealing with, we have small, as in this plot, but pretty classical systems. Well, there is one example from a billion of possible examples. It's molecules which are put into carbon nanotube. Despite the fact that you see atomic scale, these molecules are massive, so that with best approximation, they obey classical laws of motion. And again, we find equivalence. In exact terms, we find equivalence between statistical physics in classical statistical physics in n dimensions and quantum mechanics in n plus n minus 1 dimension. Right? One could say that extra dimension is time, but yeah, we can argue about this. Whether it's really time or something which we want to be time, but it is not. Right. To get to the topic, we've got to shortly repeat what we know already, or whatever, almost know but forgotten, about facts about Schrödinger equation, quantum mechanics, and classical statistics. right? That would take a kind of at least 1/3 of this lesson. Then we find equivalence between what we repeated, what we have formulated. We will find equivalence in two ways. Well, these names you might have heard, but well, at this first transparency, they do not mean much, just ways, which I will explain. Right, and again, I guess it's, for me, it's the best and reasonably simple illustration of the enormous power of theoretical physics. Fine. So let's just be classical quantum or quantumly classical. Let's try to understand how does it work. First of all, about Schrödinger equation. You might smile because, yeah, you have heard about this perhaps 10 times, if not more. I will talk about Schrödinger equation for one-dimensional motion per particle, single particle which moves in single dimension. To this end, its wave function is a function of a single variable. All right. As all quantum mechanical wave function, it obeys an evolution equation, which is normally called Schrödinger equation. All right. Well, it's evolution because it gives you time derivative of wave function based on its value at this time moment. So if we know wave function at time 0, we can iterate it by small steps, computing derivative at each step, and we know the solution for any child. Good. What is there? What acts on the wave function? It's an operator. Operator, it takes function, it returns function. This particular operator is called Hamiltonian. And, well, we know perhaps that in this setup, most interest are stationary solutions for wave functions. And those are given by eigenvalues of the Hamiltonian, which one would call energy levels. Here it's a plot. There is a particle in some fancy one-dimensional potential. And right, there are solutions to Schrödinger equation at certain energies, which I gave by lines. All right, as I mentioned, today I will talk about single variable x. It could be generalized for two variables, but then statistical mechanics also will become more complex. So let's stay with that. Right. An example Hamiltonian, that's also which you know. It's made from kinetic energy and potential energy. Kinetic energy is a function of momentum operator, and potential energy is a function of coordinate operator. It is accustomed to write Schrödinger equation in X representation of many. What does it mean? That operator of X is just multiplication with X. Operator of momentum becomes derivative with respect to X. And this is the Hamiltonian. And with that, we come to Schrödinger equation. All right. I bet it's all familiar to you. If you have noticed a detail which did not bother you when you have heard about this first, you might formulate a question. But that all seems transparent. Just, yeah. It is a barrier, if you kind of get used to classical physics, it's a barrier to start to think quantum mechanically in terms of wave functions, stochastics. Well, but here it's just something which one can adjust to. Right, no questions about Schrödinger equation. Actually, did I start the recording? Let me check this. Oh yeah, I did. Fine. So let me talk about statistics, and eventually, if I formulate statistics at this level, at the level which I put to this transparency, well, it does not matter much whether the system under consideration is quantum classical. What is important that this system can be in a set of states. Energies of these states are given. Right, it could be classical energies for a classical system, or it could be quantized energies which have to be computed by quantum mechanics, but well, that's remains. Right, essential assumption, which would actually allow me to make the analogy, is that the system is in thermal equilibrium. Then we know what happens. Perhaps you have heard this formulation in alternative ways. For me, it is convenient to formulate the main postulate of statistical physics is like following. The probability to be in a given state is proportional to Boltzmann weight factor, which is exponent minus energy divided by kBT. Right. Normally people don't write kB, but well, it's a choice of system of units. Right. Then I want to talk about partition function. And here I want to stress perhaps what your teachers did not stress to you. In many areas of physics, you would have to calculate whatever, measure, understand different quantities, and only when you take it together, you have full understanding of the phenomenon. The structure of statistical physics is such that partition function of a system provides you ultimate answer to all questions concerning the system in thermal equilibrium. You don't have to learn anything but partition function. So let me go with examples of this. Right, so first free energy. Free energy, to remind, is just log of partitioned function times kBt. How about average energy? Well, it's kind of difficult to comprehend or recall from the course of statistical physics, but this free energy is not average energy in the system. Average energy is given by derivative of the log of partition function with respect to certain variable, which is in this case, reverse temperature. And it is not just a singular fact. It is not just a occasional property. Average of any quantity in statistical physics can be computed in the following way. Right, suppose we have variable x, which could be whatever, pressure, magnetization, any quantity which you can imagine. For each variable, one can find a conjugated force. Conjugated force, what does it mean? It means that the force and the variable come to the energy, come to the Hamiltonian in that particular way. If x is displacement, F is actual force. If x is volume, who would dare to guess what is the conjugated force? Oh, you know that. Good. That encouraged if x is pressure. What is conjugated force? Very good. That makes it the task. One can make such pairs from any values like magnetization, then conjugated force is magnetic field, and vice versa. All right. So for any value we can do so, and we just add to energy this term, x with conjugate force, and then we differentiate the log again, or free energy, which is proportional to the log, and we get average value of the variable we are interested in. Right? So what we need is just partition function, and it is a function, it has arguments, and we can differentiate with respect to these arguments. So with this, it provides ultimate answer to all questions in statistical physics. All right. It was very general formulation of statistics. Again, it doesn't matter whether it's quantum or not. Let me remind a couple of more specific settings. Let me talk about Ising or Ising model Bose translations. A good. That was a German person who immigrated to United States, and that problem was solved in his PhD thesis exactly 100 years ago. All right, to give details, the topic of this thesis is supposed to be much more challenging. It was about magnetism in solids. But well, okay, there are students of different qualifications, so the problem had to be simplified, 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 till really ultimate simplification. It became one-dimensional instead of three-dimensional. And instead of magnetic spins, we would just have spins which are classical and which can be directed in two possible directions. And in that formulation, it appeared to be solved by using or adding, and we will, that model appears to be archetypical for many and many models of statistical physics. Archetypical means that everything can be done by sophistication of Eisen model, by adding more variables per site, by making it two or three dimensional. So it's really a kern of statistical physics. Let me just go through details. What is this? We have one-dimensional line with discrete nodes, which will be labeled by I. Right. So that's supposed to be y-axis. Right, and in each node, we have spin, which can be in two directions. That spin is supposed to feel magnetic field, and this is on-site interaction. A spin feels that without consulting its neighbors. It's only between magnetic spin, magnetic field, and this particular spin. No interaction. And if there's no interaction, Eisen model would be just a collection of independent spins, easy to solve. And well, there is a Boltzmann factor associated with this interaction. What makes it less trivial is the interaction between neighboring spins. This is one. Depending on sign of coupling constant J, this interaction can favor parallel or anti-parallel spins. All right, with this we can write down partition function. It is simple. We need to write it. We need to sum up over all possible spin configurations and compute energy for each configuration and put it into Boltzmann factors. Here they are. So we need to multiply it with inverse temperature. And here we have magnetic field interaction. Here we have nearest neighbor interactions in Eisen model. Fine. We kind of solve one-dimensional model today, so I don't bother you with the solution at this moment. Just curious, what do you know about Eisen model? Have you heard about it? Did everybody or just you? Oh, okay. Good. So in one dimension, Eisenmodel can be solved. In this is was a PhD exercise. For 2 dimensions, it also can be solved. It's very difficult mathematical method, which has been it has been done by Professor Onzager somewhere in 50s. People wanted to solve 3-dimensional Eisenmodel, and that didn't work. It doesn't work still, and I guess it will not work for perhaps several millennia. There is something which you cannot do. It's teasingly simple. You just have a couple of parameters or whatever. If you only have a coupling parameter, that would be a great achievement if you solve it. My favorite story about 3-dimensional Eisenmodel has very little to do with physics, but shows physical significance of that. There was at some time assistant professor in China, young guy, Yilu was his name, and he kind of studied physics, he taught physics, but then something bad has happened in China. A story has been, which has been called culture revolution. So instead of university, that guy has been sent to a distant village where he had to help farmers, basically to grow carrots or something like that. He was deprived of the family. He was allowed to live in such rather strange conditions. That lasted for 8 years, right? And he used to tell everybody that the only thing why he survived as a person, why he didn't commit suicide or just got crazy, was that every morning he was trying to solve 3-dimensional Eisen. But after these 8 years, he still didn't have anything even to publish. Fine, that was as a model. Let me get to something which you might also know, or like Eisenmodel, you have heard about this. Let me talk about what is called Landau Hamiltonian, or in general, Landau's theory of second-order transitions. I wanna make some steps, very common steps that are frequently made in statistical physics, to get from discrete variables and discrete space to continuous variables and continuous space. Right? How it can be done? It can be done by, simplest way is to do it as coarse graining. So for instance, instead of a single site, we just take 10 sites, right? Then instead, and what is the variable to characterize these 10 sites? It has 2 to the power 10 values. So it can be safely regarded as a continuous variable. It has very many discrete level values. That is continuity in the variable. Continuity space is simply just look at configurations which are smooth in space. With this continuous variable, you can just you can average over configurations where magnetization changes abruptly. And all right, after this coarse graining procedure, what you will have is a function, continuous function of x, which is variable, magnetizational case, versus y, which is variable which labels the nodes. Very good. Let us try to get some model free energy for this variable. There are terms which are very natural. It would give us energy as a function of magnetization in each point separately. Magnetization costs some energy, depending on magnetization, and this is purely local quantity. Well, if we just leave this, it won't be enough. Why? Because at the next node, at the neighboring point, magnetization can be very different because of the fluctuations. Average value would be the same, but in the configuration, it would vary much. We need to introduce energy find for change of the variable. And this is done by assigning gradient term. So it makes energetically unfavorable to have gradients in the variable. It would rather be smooth. Fine. Now, with these two terms, we still can think about concrete forms of this U tilde. And what Landau has suggested is a form which is comprised of two terms, polynomial terms, x squared and x to the 4. So, and there's a parameter, basically coefficient in front of x squared terms. Right. So why it is so interesting and why it describes phase transitions, critical phenomena. All right, if T is positive, the potential is like this. It's a symmetric potential with respect to inversion of x to minus x. And the only solution is the particle in the middle, the particle at x equals 0. And if you don't think carefully, you could say, well, it's universal, it's always so. There is symmetry in the system, and the realization will be always symmetric. The point is, if T is negative, the potential is like this. It remains symmetric, but its minima, its solutions, so to say, are not symmetric, right? In that case, we have the minimum, and magnetization can be either on the left and on the right. If we talk about magnetic transition, this is the phase without magnetization. And this is magnetic phase, the spontaneous symmetry breaking, which occurs at small t. Good. Combining these elements, Landau potential, and gradient terms, one can build up fascinating, important theory of critical behavior in the vicinity of second order transitions, theory of critical exponents. We won't go to this direction, just let me mention that it's one of the biggest advances of statistical physics of 20th century. Good, that was Landau Hamiltonian. Any questions about this? Who have heard about this, at least about this picture? You?
I saw it as a Landau Ginsburg for superconductors.
Oh, you follow very special education.
Yeah, I mean, it looks a lot like that.
Yeah, it is like this. Physics is universal, and what Landau Ginsburg have proposed for superconductors is a modification of this Hamiltonian, where instead of X, one has a psi, complex valued parameter. Also, there's electromagnetic energy. But well, it indeed one of the applications of Landau Hamiltonian. But Landau Hamiltonian has more generic range of applicability. You can describe it this Hamiltonian whatever you need. Magnetization transitions, critical point of water, ice, vapor system, almost everything. Any situation when symmetry breaks. Fine. Let us see how we're doing in time. Good. So perhaps I can start with the stuff. And we now want to move from quantum mechanics to classical physics. And what we do is a strange procedure which is difficult to motivate, but I will try. Fine. First, to describe the situation, to describe our problem. We have quantum mechanics. We have one particle Hamiltonian of a familiar form. We want to compute thermodynamics of this quantum system. And we write partition function for this. Now we have a little bit of a problem. It is an operator, and if you cannot diagonalize it, you cannot really compute what you have here. We want to find an interesting representation for this partition function without actually computing it, but well, it will be helpful by computations, of course. And the procedure, as I said, it's a bit counterintuitive. We cannot deal with this piece exponent minus beta h. And the trick is to slice it in smaller pieces And instead of a single exponent of the kind, consider big product of smaller exponents. Right. If you look at it logically, it doesn't make any sense, right? We cannot deal with a single object, and if we multiply it, it will still remain the same object. So it looks like we have complicated our problem immensely. That's not really so, and I could not find a good analogy for a long time in my life. Till by some chance I got to a workshop on preparation of sushi. You know what sushi is. And only on this workshop I have actually understood that sushi comes in form of very long rolls, about 1 meter long. You can make it, but you cannot swallow it. If you want to swallow it, you slice it. And only then you can deal with the problem. That's something which we're gonna do now. We will try to swallow it slice by slice. Right. So, first of all, let us introduce a slice operator. Shall I explain why any operator in one dimension can be regarded as a function which depends on two variables? Quickest way is to recall that any operator is a matrix. Indices of this particular matrix are values of x. Fine. Well, discrete continuous doesn't matter much. All right, that's why the matrix is represented as a function of two variables. That's what we do. With this, we can swallow this big roll slice by slice. Suppose we start with some function which acts on these operators, and we have computed the result till slice I. We can go to next value of wave function by this relation. Right? So wave function is known by up to here. If you want to know it at this moment, we just apply this operator again. Here, but it eventually looks pretty much like Schrödinger equation. How come? Let us go to the limit of very thin slice. Then we can expand this exponent. Mainly it's 1. And the rest is h times delta t. Good. We substituted here. And in the limit of delta t to 0, we obtain an equation which looks pretty much like Schrödinger one, with only a little detail. Who has noticed this little detail? What is the difference? Yes, see?
There's no I.
There's no I, there's no imaginary unit here. That's why people prefer to call this parameter imaginary time. And indeed, it's not really a real physical time which we live in, right? It is some extra parameter we introduce to solve quantum mysteries. And okay, although it looks like time, the absence of imaginary unit clearly tells us no, it's not, it is something else. But it's convenient from time to time to think of this as really time which goes. Time goes, so let's have a 5-minute break at this point.